Hey there, and welcome to video 3 of BattleZips-Noir. Today we're going to be looking at the Noir language itself and the underlying project structure. Look at how files are organized and wrap the video up by looking at the roadmap for features coming soon. So let's go ahead and jump into the video. We're going to start by looking at how a Noir project is structured, and by far the easiest way to create a new Noir project is running the Nargo new command, which I'll go ahead and demonstrate right now. So we'll do Nargo new, and then we can call this project an arbitrary name. We'll just do Noir Ling example in this case. Okay, and now we can see a project directory has been made. Inside, initially, we have a nargo.toml configuration file and a source subdirectory that contains the main.noir file. Now, just jumping into this real quick, starting a new project will initialize a simple Noir circuit for you. Each project has one main function, and that's kind of the entry point for the circuit. So this is where all of your public and private inputs will come from. And as we can see here, we have a X private input that's of type field, and then a Y public input of a type field. You can see the distinguisher here is this public keyword. And then finally, all we are doing in the circuit is constraining that X is not equal to Y. And for those who are confused with this terminology, we are going to jump into the language a few slides down. But just for now, I'm going to demonstrate what a simple circuit looks like upon project creation. So going back to the slide, two other important files we need to generate for our Noir project are the prover.toml file and the verifier.toml file. And these are going to be our files that maintain inputs to our circuit. So the prover.toml is going to contain all public, private inputs as well as return values if they may exist. And then our verifier.toml file is only going to contain public inputs. And generating the two files is really easy. Again, we'll use Nargo, but this time we will use the build command. Oh, and actually we have to hop into our project directory first. Let's go ahead and do that. And now we can see these files have been generated. So we have X and Y here in prover. Again, prover.toml will contain both public and private inputs. And then in verifier, we have our one public input, Y. Real quick, let's just demonstrate how we can prove circuits. So put in 3, put in 4 for Y, and put in 4 for Y here, just to demonstrate how we would prove with Nargo with this basic circuit. So now we'll write the command nargo prove, and then this right here can just be an arbitrary name for our proof file. We'll just use p nargo.prove, and can see now a subdirectory has been generated called proofs. It contains a p.proof file, and the fact that it was generated shows that our inputs met the constraints properly. Just to provide an example of what it would look like if we provided incorrect constraints, go ahead and change Y to 3 to match X. We can see could not satisfy all constraints because obviously X is 3, Y is 3, they are equal to each other. So this is always going to fail. But yeah, going forward, we have generated our proof file, and now we run nargo verify, specify that proof file. And we can see it's false in this case because, again, all constraints were met. So let's go ahead and change this back to 4. Let's generate the proof again. Now we can see proof has been successfully verified. Awesome. So yeah, this is the main idea right here. As I mentioned before, we only want one main function per Noir project. If you had a related circuit, as we do in the case of BattleZips, that isn't going to have the same exact inputs as this one, what you would want to do is jump back to the root directory, run the nargo new command again, create a new project directory, specify the circuit inputs there. I would recommend, in the case of the BattleZips-Noir structure, you contain all these project files under a circuit directory, but we will show that off when we jump into the actual code in the next few videos. Okay, so now we're going to touch on an acronym that's been thrown around quite a bit, and that is Acir. Acir stands for Abstract Circuit Intermediate Representation, and the reason we use it is because Noir is proving system agnostic, fundamentally. For those who have had prior exposure to ZK and written their own ZK applications, you might be familiar with terms like Groth16, Planck, or Marlin. And these are all different proving systems that ultimately generate zero-knowledge proofs with their own set of parameters and unique setups. And Noir allows you to port in a proving system of your choice in their configuration files, in their nargo.toml file, or I'm sorry, their cargo.toml file. So what Acir basically allows you to do is, irrespective of what proving system you use, you go ahead and write your circuit in Noir, and it'll always generate an Acir file, no matter what proving system you use. And then that Acir file can be taken, used in a Node application, ported over to a front end, which we will demonstrate later in this video series, and be used to then generate proofs from that compiled code. So generating Acir from the Nargo command line toolkit is very simple. All we have to do is run nargo compile and then specify a name for our Acir file. Go ahead and demonstrate this right now. We'll just specify the name as P again. Boom, there we go. We can see we have now generated an Acir file. And we'll touch over how this is then used later on in the video series, but as of right now, just want to demonstrate how this is done with Nargo. Okay, so moving on to an overview of the language itself. Noir is a language derived from Rust. It was built using Rust and has inherited a lot of the code characteristics. But as a ZK DSL, it's a bit more limited in features than Rust, but it makes sense because Noir is not meant to be a general programming language. It's simply used for using zero-knowledge circuits to generate a constraint system. All non-bracket statements must end with a semicolon. That includes constraining two values, function calls, variable declarations. If statements and function declarations do not need a semicolon. Although it is worth noting that as of right now, a for loop does, but this is going to be removed in a coming update. And finally, just to see whether or not our code is syntactically correct, we run nargo compile, and alongside generating the Acir file, it'll tell us whether or not our code will run successfully. So now we're going to have a look at what data types Noir provides. And before jumping in, it's worth mentioning that all types will ultimately compile down to a field just due to the nature of constraint systems. But Noir abstracts away from this and provides us with more familiar developer-friendly data types for those who may not have had exposure to ZK development before. But starting off with primitive types, we have the native field, we have the integer data type, and we'll just go to the Noir Gitbook real quick to go over this. So all an integer data type is it's a field with a range constraint put over it, and you're specifying the size as U1 to U64, where the number represents the bytes. And the U actually stands for the fact that as of right now, Noir doesn't actually support signed integers. So you can't have negative numbers within circuits, although this is on the roadmap and you can expect it to be implemented in the near future. Moving on, we have Boolean variables, pretty straightforward, true or false. Noir also has support for compound data types such as arrays, tuples, and structs. We'll just go over these quickly. An array, I'm sure most of us have seen before, but what's worth noting is as of right now, you cannot have multi-dimensional arrays. You can only have single-dimensional arrays consisting of primitive data types such as integers or fields. Structs I think most of us would be familiar with, call them objects in JavaScript, but structs are also native to Solidity and Rust. And these are constructs containing key value pairs, where the key is an arbitrary string named to your choice. And then the value is going to be some specified type, as we can see in the definition of the struct here, and then the assignment of a struct to a variable. Key values, assignments on the right-hand side. And then lastly, tuples, similar to arrays, but instead of being held in square brackets, you have them in parentheses. And the way you access a tuple is through dot notation. So you access a tuple by doing dot index, b5 in this case, dot 3, that would get you the value 8. And there's definitely more to talk about when it comes to data types, but just for the sake of time, we're going to continue on and dive into variables. And for those who want to learn more, I highly recommend you check out the Noir Git book and read up on that. So moving on to variables and mutability. Variables are declared in Noir using the let keyword. So if we want to create a variable called x, we would say let x. We're assigning it a value of 2, so let x equals 2, the correct syntax. Variables are immutable by default, and the way we specify mutability is using the mute keyword and putting it after let. And it's worth mentioning that mutability is local only. So if we have this example here in the Noir Git book, we specify a variable x is assigned to 3, and then pass it to a helper function where the input's mutable. The variable reassignment is only going to be valid in the helper function. Outside of helper, x will still have a value of 3. And finally, the last topic we're talking about when it comes to variables is comp time variables. And these are pretty much declarations that say a value is not going to change throughout the duration of a circuit execution. It's another way of calling a variable constant. And right now, it is currently limited to primitive data types like integer and field. Moving on to functions, we specify a function with the keyword fn, and functions may or may not have a return value. If you choose to give a function a return value, all you do is pass it an arrow at the end and specify the return type after that arrow, like so. And when it comes to returning values, we can either implicitly, if the last line of a function contains the value needed to be returned, we can implicitly return by removing a semicolon at the end of the function, or we can explicitly return by specifying a return keyword and putting a semicolon after the value. And then the last thing worth mentioning is the main function can specify whether a parameter is public or not. And we can also specify whether a return value should be public or not. And the way we do that is just prepending pub to field right here. Okay, so moving on to conditional statements and control flow. Noir currently does support loops, but it only supports for loops and with limited functionality at the moment. So one thing that was tricky at first is that the range needs to be known at compile time. So to give an example where this might be problematic, you have, let's say in the case of battleships, we have 5 different ships, each of different length. And we have a loop, a nested for loop. We're looping through all 5 ships and also trying to find the length of each ship in the second for loop. You actually have to know the value prior to that. It can't be something determined by the index in the outer for loop, but that is something currently being worked on by the Noir team. But for now, you have to declare the range explicitly in the circuit. It can't be something variable. For loops must be ended with a semicolon right now. This is something that is currently being worked on by the Noir team, but just something unexpected you have to watch out for when compiling your circuit. And then if-else statements, pretty straightforward, like you would write them in another language. Parentheses are optional in the if statement. I have them right here just out of habit, but you can also have the comparison outside of parentheses. So now we're going to talk about constraining values, and constraining in Noir is super straightforward. All you need to do is explicitly put the constrain keyword and have a Boolean comparison on the right-hand side. So this would work for equality, inequality, greater than, less than or equal to, greater than or equal to. And just to show an example in a function, very simple function like we had before when we created our project. When we pass in an x field and a y field, we're simply constraining whether x is equal to y or not, or that constraining that they're not equal to each other, I should say. So now we're reaching the end of the video, and a few things we're talking about before we wrap up are features on the roadmap. The first topic we kind of touched on before, and that is the ability to have signed integer types, because right now Noir has no support for negative numbers. But that update will be coming soon, according to the Noir Gitbook. The Poseidon hash implementation is also coming soon. I believe a grantee is working on it. And for those who are not familiar with Poseidon, Poseidon is a snark-friendly hash function. Others that might be well known are MIMC and Peterson, but expect that sometime in the near future as well. And two other values that we kind of touched on before, or we touched on ranges before, but not array indexing, are just non-comp time values for specifying arbitrary ranges or accessing an array at an index, let's say, that's dependent on one of the inputs from our main function. That currently isn't possible, and there's a lot of stuff we could potentially use with that type of functionality, but that is on the roadmap currently and will be coming in the near future as well. And then lastly, one of the most exciting things coming in Noir is recursion. And what recursion allows us to do is verify proofs within other proofs. And this leads to massive gains in computational efficiency and really opens doorways to applications that weren't possible prior to this. So super excited to see when this is implemented and how it can be applied to BattleZips. All right, so that concludes video 3. And in the next video, we're done with the preliminary information and actually going to look at the project organization for BattleZips-Noir, as well as touch on how do we actually play a game of Battleship, and then look at a live demo of the app and explain what technologies are being used and what's going on under the hood, so to speak. But thank you for watching video 3, and excited to see you for the next one.